Yeah, I got a lot on there, okay.
August 9th, 2015. I'm in this book again. There's a whole hell of a lot of stuff in here that I'm going over. But A Star Called the Sun by George Gamow. I'm on page 69. Now I know what people might say, oh, you're reading a book that was copyrighted in 1964, so it's out of date. I'm pretty sure Newton's equations were copyrighted in like the 18th century, so that argument is bogus. This is actually real stuff here. This applies to what we're doing even today, as well as applies to stellar metamorphosis, and I will explain why in a few minutes. Up here we have title, temperature, and gas pressure to determine the degree of ionization. Now, ionization, as far as I know, I could be wrong, really only goes over the electrons that orbit a nucleus. Now, whether the electrons are formed as a byproduct of some process and they don't actually exist inside the atom, or if electrons are actually particles or waves, I'm not arguing for all that stuff. All I'm arguing is a simple representative understanding of the relation of gas pressure, of actual pressure to the degree of ionization. So you have your electrons. Now, I know calcium, Ca, has 20 electrons per atom, so this isn't the right molecule, but this is just as an example. Neutral calcium has, all their electrons in there, and when you take an electron away, it becomes positive, has a single degree of ionization, meaning it is singly ionized calcium. It's ionized to 1 degree. And then you have doubly ionized calcium, and even quad ionized, and it just keep on going to based on however hot the star is and how low of a pressure there is provided on the star. You'll see that this graph right here is just the percentage of atoms, however much the ionization is inside the atoms. Here is the temperature in 1,000 degrees Kelvin. So this is 1,000 Kelvin, 2,000, 3,000, 4, 5, 6, 7, and 9,000 Kelvin, which is really, really hot. And the pressure of this plasma, yes, I said plasma, it's not gas, because once it's ionized, it becomes a plasma, is 1/100,000th of an atmosphere, standard temperature pressures of the Earth, meaning it's basically a vacuum, basically mostly vacuum. And what you'll see here is that you have 3,000 degrees Kelvin, and then once you get to 3,000 degrees Kelvin, some of that calcium becomes singly ionized, meaning the electron gets ripped away from it, and it becomes positive, meaning electromagnetic forcing will start to take place because it can conduct electricity. It starts acting like an electrolyte. And then as you get hotter and hotter and hotter, see 5,000 degrees, the entire thing is singly ionized calcium. But then if you keep on going, you can get different degrees of ionization. So you have higher stages of calcium ionization past 9,000 degrees, given this very vacuumous environment. And the main point I wanted to go over is that you had the amount of heat required for the thermal release of the electron. Well, it decreases. So if you have the pressure of the electron gas increasing, you have to get it even hotter for there to be any ionization. So given the electron gas is pressurized even more, you have to get it hotter. So say, I don't know what the actual atmospheric pressure is, but say you just have it as 1 Earth atmosphere, okay? Now I know that's wrong, but for example, that calcium would need to reach at least 9,000 degrees Kelvin in order to become ionized. Now, I look at lightning bolts, because the pressure is so high in the atmosphere that there has to be a whole shitload of energy a lot of heat, I should say, to ionize all that atmospheric, all that atmosphere as the lightning bolt goes through the atmosphere. Now, if it wasn't that pressurized, then there would be a lot easier. It would be a lot easier for that atmosphere to ionize all the calcium. So basically, I'm saying this in too many words, but when you increase the pressure, you also have to increase the temperature to ionize the calcium to higher and higher states of ionization. And this is important to understand because in the theory I'm developing, you have a hot star. It's very vacuumous on the exterior. Now I know there are different ideas out there on the internet about the sun being this or that or whatnot, but I'm going to take the stance that the outer atmosphere of it is mostly vacuum. There isn't a surface on it. It's mostly vacuumous plasma that's electromagnetically forced. And there's a lot of thermal energy in there. But when you take that hot star and you start to condense it, and the gas starts condensing and going at higher pressures, and the star begins cooling, it takes a lot more thermal energy for it to ionize that material. So it can't recombine and obviously release a photon as the sun's doing right now with a lot of its plasma. So what's going to naturally happen is as the pressure increases and the star collapses upon itself, what happens is that the ionization is going to decrease. So meaning the material that recombines the first and can sustain its ionization at higher and higher temperatures, that's going to be the stuff to recombine the last, meaning it's going to stay up in the high atmosphere longer than the other material. I think I said that right. So basically, it's a whole hell of a lot more complicated than I originally thought. I kind of figured it's going to be this complicated, but I noticed this saying in there in the book. I wanted to write the entire thing down for people. As Gamal said, now this isn't in quotes in the book. I just took it out of the book and I put it in quotes myself. But the entire picture of the effect of changing temperature, delta T, and pressure, delta P, I'm sure pressure probably has a different symbol, on the state of ionization of a gas formed by a mixture of all different chemical elements is extremely complicated, but not beyond the understanding of a person who knows the laws of atoms and is willing to spend some time on it. Whew. Yeah, because basically when you have this heated plasma with different degrees of ionization, when it recombines, and say that high degree of ionization of calcium combines with iron somewhere, holy cow. Then you have oxygen in there, and you have nitrogen in there, and you have silicon, Si I think, and then sulfur is S, and then you have, bismuth and cobalt and chromium, and you have all this stuff going on in there. It's an extremely complex process as the star starts cooling. This is genuine astrophysics. Like this guy here, the Indian astronomer Meghnad Saha, he developed the theory of the solar atmosphere, and he was just trying to find out, this guy right here, he was just trying to find out the composition of the atmosphere itself, which, he wanted to relate to the entire structure of the sun, and I think that's okay, but I don't really know about that. I have to just try to make my theory work in the fact that the sun cools and shrinks to become a red dwarf. That's the next stage, so I have to get more information. I have to start studying red dwarfs now, but you have all these different elements in there, and they're different percentages by volume, and milligrams per square centimeter of the sun's surface. Like, I have to include all this stuff in there. And it's no wonder why scientists haven't done it yet, because basically the sun is just like stationary. It's not evolving that rapidly. But now that we have a theory, and that's what I'm working on, of stellar evolution, complete stellar evolution, we can literally look at the Earth itself. I know the Earth, and it has its own, you know, there's material right there, there's material right there, there's material right there. And we can literally like look at it and to see where they would fit inside of something like this, inside of gas giants. And obviously the gas giants can be reverse engineered when we get more information on their atmospheres to figure out what's going to happen to the sun and even larger, more energetic stars. But basically, that's it in a nutshell. I think what I want people to understand the most out of this specific talk is that when the pressure increases, the temperature has to increase as well to keep that same level of ionization. As well, when you look at stars, don't view them as something that stays as a perfect plasma or it has just, you know, this amount of calcium, but not any of this and not any of this in there. So yes, there is neutral calcium in the sun. There is singly ionized calcium. There is higher stages of calcium ionization in the sun. So to look at this as, you know, this will be a plasma obviously, and this is a gas, and this is, you know, crazy. You have this going back and forth inside the sun as it loses energy, as the ionization recombines and then it reionizes again from the thermal collisions inside the solar atmosphere. So it's more like a back and forth kind of thing. So I think it's more healthy to look at that in a kind of give and take feedback kind of thing, depending on where the star is inside of its evolutionary path. But as well, this back and forth feedback loop changes when you increase the pressure on that material. So the back and forth feedback loop kind of diminishes, and then, you know, you have that neutral calcium. But then again, you have other elements, so they neutralize with the calcium as well when it was ionized. So then you have, you know, molecules forming as it rains down into the interior of the star. And well, basically, that's the whole idea. And also keep in mind that there are different degrees of ionization. Like, I remember I saw iron in there, and it had like boom, 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 boom. Like, what was it? 9, even 10 degrees of ionization. So all of its outer electrons were completely ripped away, to where iron literally looked like some other element entirely different from it. But that would be hard for solar spectrums to be deciphered. But anyways, there you go.